Okay, let's derive what we usually call the terminal velocity. Before we do this, excuse me, let's review freefall. Let's imagine that we have an object in the air that we release at t is equal to 0, and let's imagine that the initial velocity is 0. As we let it go, we know that this object will be accelerated at a constant rate, because we know that the acceleration is 9.81 meters per second squared in this particular direction. So we know that every seconds, this object will pick up 9.81 meters per second. The second, it will be twice this amount, and so on and so forth. Similarly, we know that the position will increase over time. So if we want to plot the velocity versus time for such motion, we know that this graph would be a linear line starting at 0, since we decided v0 to be equal to 0. If we try to use Newton's analysis on this object, then we know that there is only one force acting on the subject, which is the weight, which is the one that causes this acceleration with this particular value. Okay, now let's imagine the case where we have drag force, which is another name for the frictional force in a medium. Let's call this force Fd, and let's assume that this force can be written as a constant k times the velocity. So this force depends on the velocity. So this functional form of the drag force tells us that if the velocity is 0, this drag force is 0. As the velocity increases, the magnitude of this force will increase. The property of the drag force shares the same property as the standard frictional force concerning its direction. So if the direction of motion is towards the right, the direction of the frictional force will be towards the left. And again, based on this definition, the faster the object is moving, the higher the magnitude of this drag force. So let's imagine that we are considering the same situation of an object sitting at rest at t is equal to 0. At this particular time, we know that the only force acting on this object is W, because since the initial velocity is 0, the drag force is 0. Then at some later time, t is equal to t1, we know that this object will have picked up some velocity. Therefore, there is now a second force acting on it, which is our Fd, in addition to the original weight. Then at t is equal to t2, which is bigger than t1, the velocity by that time will have increased even more. Therefore, we know that the drag force would increase accordingly in magnitude. So we can guess that at some point, t is equal to t3, the magnitude of the drag force will take the exact same value as the magnitude of the weight. And this, according to Newton's second law, is telling us that the left-hand side is equal to 0, which means that after t is equal to t3, the acceleration will be equal to 0, which means that the velocity will reach a constant value. So now we're dealing with a case where we start at v is equal to 0, we let it drop, the only force acting on it is a weight. As the object starts to pick up some velocity, the magnitude of the drag force would increase. So since this object keeps being accelerated, the velocity will increase even more. As the velocity increases even more, the magnitude of Fd will keep increasing, and this process will keep going until the magnitude of the drag force will equate the magnitude of the weight. And at this particular instant, the sum of the two forces acting on the system will be equal to 0, therefore the acceleration will be 0, and therefore the velocity will reach its maximum value, which we will call Vt. So let's look at this particular time. Let's look at the time at which the magnitude of both forces is equal to 0. We will have, if we decide this to be our positive y direction, we will have Fd minus W is equal to ma. Since the object is being accelerated down, my acceleration is negative. As I replace the functional form for the drag force, I can write Kv minus mg is equal to minus ma, and I'm going to change all the signs. Okay, so again at this particular point, we know that the magnitude of the drag force is equal to the weight. Therefore, this must be equal to 0. As we solve for v, we will end up with mg divided by k. So this is the velocity that the object will reach as the drag force increases until its magnitude equal the magnitude of the weight. This is what we will call the terminal velocity. So now we can plot this particular behavior. We started at v0 is equal to 0, and we know that at t3, which is a time after t0, the velocity will reach a constant value vt, which is mg divided by k. So what I'm interested in is, let's try to figure out how the velocity will go from point A to point B. Is it going to go like this? Is it going to go like this? Is it going to go like this? Let's try to figure out the full functional form of the velocity as a function of time when we consider the drag force. So let's go back to the initial analysis. We have the object, we have the weight, we have the drag force, whose magnitude changes depending on the velocity. And this system is being accelerated down. So as we write sum of the forces is equal to ma, we will have kv minus mg is equal to minus ma. Let's change the sign on both sides. So this is the general case for all times between t is equal to 0 and t is equal to t3. To keep this problem general, we will assume that initially at t is equal to 0, the velocity can take an initial value, v0. So now we are facing an equation that we need to solve for v. The second term is a constant, but the term on the right hand side depends on the acceleration. So let's try to figure out a correlation between acceleration and velocity. From kinematic, we know that a is equal to dv dt. So let's plug that in. Now we have minus kv plus mg is equal to m dv dt. So now all we need to do is solve for v. But we realize that we have a v term, a constant term, and a dv. So at this point, we need to do what is called separation of variable. We're going to try to find a trick to separate the variables from that equation. So we're going to try to put all the v's in one side and all the t's in the other side. The reason why we want to do this and use this technique is because the other way to solve for this is to use partial differential equation. So we're not going to use the method of differential equation, we're going to use the method of separation of variables in order to allow us to solve for this equation without having to use differential equations. So what I could do is I could multiply everything by dt in order to make the dt all by itself on the left hand side. So let's do this. I'm going to have dt times minus kv plus mg is equal to m dv. But I still have this term that bothers me, so let's take it out and let's move it on the right hand side. So I'm going to divide the whole equation by this term. So what's left on the left hand side is my dt, which I have now isolated. And on the right hand side, I have m dv mg minus kv. And at this point, I'm very happy because I have managed to separate the time on the left hand side and the velocities on the right hand side. So now I can integrate. And this just resumes itself to a math problem. So my initial condition is going to be t is equal to 0, and I'm going to integrate all the way up to time t. Now this is mathematically incorrect, so I need to change my dummy variable to another name. Let's call it t prime. Similarly, v is my dummy variable on the right hand side, so my initial velocity for v is v naught, and I'm going to put my variable on the top. Same as the left hand side, if I have v here, I need to change this to say v prime, and it's mathematically correct. So the left hand side is very easy. This will give me t prime that needs to be evaluated between t and 0. Now on the right hand side, I can make it a little bit prettier. I can factorize the m out, and I can take the k away. Okay, so I took the m outside of the integral because it's a constant, and then I factorize k from the bottom part. And once I've do this, then I can recognize easily, hey, this looks like results from calculus 1, which is dx a minus x, and this should give me minus ln of a minus x. So I could use these results. So let's do this. In this particular case, a is equal to mg over k. So I'm going to have t is equal to m over k times minus ln of mg divided by k minus my v prime, and then minus ln mg divided by k minus v naught. Okay, so this comes from integrating this equation, this integral, and evaluate it between v and v naught. Therefore, this must be a v. I'm sorry. Okay. So let's get rid of the negative sign. I have t, mk. I have ln of mgk minus v naught plus ln mgk minus v. So I switched those two terms around and I got rid of the two negative signs. Now I remember the properties of logarithm, which tells me that ln a plus, I'm sorry, this is a negative sign, this one. Okay, and those two becomes positive right here. So ln a plus ln b is equal to ln ab, and similarly ln a minus ln b is ln of a divided by b. So I'm going to use this identity, where this is going to be my a and this is going to be my b. So the above equation becomes t is equal to m over k ln of mgk minus v naught divided by mgk minus v. Okay, so at this point, all I want to do is solve for v. So I use that trick to combine my ln, which will now allow me to get rid of the ln easily. So from now on, it's just algebra. And remember, my goal is to isolate v and express it in terms of t. So I can get rid of this term by multiplying by its inverse. I have kt divided by m is equal to ln of that big ratio, mgk minus v naught mgk minus v. Now I need to get rid of the logarithm function, and I know that to get rid of a function I just need to apply the inverse function, and I remember that ln ex is e ln x, which is x. So if I want to get rid of a ln function, all I need to do is take the exponential. So since I want to get rid of this guy, I'm just going to take the exponential on both sides of this equation so I don't change the equation, and e of ln something will give me back the something. So the left hand side will become e kt divided by m, and the right hand side will be exponential of the logarithm of mg over k minus v naught is equal to mg over k minus v. Okay, so I'm almost there. Now let's multiply both sides by this term. I have mg over k times e kt over m minus v e kt over m is equal to mg k minus v naught. Now I want to have v all by itself, so I need to get rid of the exponential. I know that e to the x, if I multiply it by e to the minus x, then I end up with e of x minus x, which is either 0, which is 1. So I'm going to multiply this equation by e of minus kt over m. This will get rid of this term. So this will allow me to have my v all by itself. So I'm going to get mg over k, e of minus blah blah times e of plus blah blah will give me 1. Same for the second term, minus v is equal to mg over k e minus kt over m plus minus v naught e of minus kt over m. Okay, almost there. Now all I have to do is move the v on this side and move all that stuff on the other side. So v will be equal to mg over k minus, and let's factorize the exponential, e of minus kt over m times mg over k minus v naught. Let's check the sign. Mg divided by k times exponential should be negative, and as I move this term on the other side, it will be negative, the second term will be positive, this one is positive. Okay, it's all good. Okay. This is the functional form of the velocity as a function of time. Let's check two limits. I know that this, as I take the limit as v goes to 0, I know I should end up with v naught. So as we take the limit of equation 1, as t goes to 0, while t is equal to 0, then e to the 0 is 1. So vt is going to be equal to mg over k minus e to the 0, which is 1. So I'm just going to have mgk minus v naught. Now this term will cancel this term, and what's left is minus times minus v naught, which is plus v naught. So this matches what we started with. Let's make sure that this functional form also matches our higher limit for t. We've seen earlier that this should be mg over k, which was our terminal velocity. So we know that we're gonna reach the terminal velocity for a high value of t. So let's take the limit as, oh, I'm sorry, that was t. As t goes to infinity, then we're going to get mg over k. Then as t goes to infinity, we have the exponential of minus infinity, and the exponential of minus infinity is 0. Therefore we have 0 times mj over k minus v naught, everything will go to 0. And sure enough, we end up with the terminal velocity that we had predicted earlier. So this equation is the one that will describe what's in between. Okay? So keep in mind, for a free fall, you know from kinematic that v must be described by a straight line of a constant slope, which is referring to the acceleration, and whose magnitude is 9.81. When you introduce drag force, such as the drag force Fd is proportional to velocity to the power of 1, then you end up with this functional form, which tells you that, so in this particular case, I'm sorry, since we started with the initial v naught, we start somewhere over here. Then we end up with an equation which is in terms of an exponential, which tells us that the velocity will increase, not linearly anymore, and then eventually is going to reach a plateau, which refers to the final terminal velocity. So after this point, t3, our object is going to be falling at constant velocity. Now the time at which this will occur will depend on many factors. It will depend on the air density, it will depend on the shape of the object. So there's going to be a lot of factors that will affect the time at which this will occur. Okay, now this was the assumption we made. The drag force technically can take different functional forms. This one refers to the case where the velocity is relatively low. As you increase your velocity, the drag force will take a different form, which is more like something times v to the square. Again, k prime is another constant. So you could redo the exact same problem, except instead of using Fd is equal to kv, then you will have in your Newton equation k prime v squared minus mg is equal to minus ma, which is minus dv dt. So you could redo the exact same procedure as we've used for this type of functional form. The only difference will be when you're going to be reaching the integration. So please look up your calculus book, try to figure out which integration results you can use, and then try to figure out the functional form of the velocity as a function of time if now you're using Fd not as a function of the velocity to the power of 1, but if your velocity is high enough such that you have to use the drag force being a function proportional to the velocity squared.